Next shows where we categorize all the signals. So it'll be two different signals in the 0 to 50 ppm range. It's going to be two different signals in the 100 to 150 ppm range because it's sp2 carbons, right? And it's going to be one signal in the 150 to 220 ppm range because of the carbonyl group.
So he's put the types of carbons in the range that they're supposed to be in. So that's really good. So 0 to 50, you have those three methyl groups, like he said. And then 100 to 150, you have those two carbons that are sp2 hybridized, carbon-carbon. And then lastly, the carbonyl carbon. So as long as you have the chart, it'll be easy to identify where they should go in the spectrum.
Right. Okay, so that's all there is to it for real. So now we're gonna do a little practice problem that I have up here.
So you don't have an actual spectrum of that?
Oh, go back, my bad, my fault.
Oh, so KJ, you didn't find an actual spectrum, like showing those two signals?
No, ma'am. I was
okay.
going to try to show it.
Okay. Can you go back to the previous one again, please? So you have two signals for each of the unique carbons, right? 0 to 50, two signals for the carbon-carbon sp2 alkene, and then one signal. Okay. So you're looking at the unique carbons, and if you have 5 unique carbons, you need to have 5 signals. So you should be able to draw the spectrum, okay? Like, give the axes and like how you did for even the NMR to be able to draw the signals in the ranges. So and these are all shown as signals. Yes, Deanna?
When we draw this, how do we know like exactly what number they go at, since it's kind of a range?
You wouldn't, you just put them right between 100 and 150, yeah. Okay. There should be ways and a table to do that, but this book and at this level, we just look at the basics. Okay.
Are we ready?
Yes, I think. Jamie, you ready?
Okay. All right, let me see how we draw on here. I wish I could draw on here somehow. I think I got it. Let me see.
I think if you stop sharing screen and then you share screen again, it tells you there's an option that says whiteboard or something like that. You can draw on that and just like draw.
He's drawing there.
Hold on, let me erase this.
Even with the whiteboard, he has to use the pens there. You should have a document camera like I do. Or write on paper, or then you have to scan it and show it.
Okay. Let's see. Let's see the paper.
Oh, do you have a whiteboard at home?
Let me go get one real quick.
Okay, like how Michaela and Hutch did last time.
I mean, there should be an annotate function.
Yeah, that's what I was going to do.
What does that mean?
And so technically I can draw on your screen. Is that working?
Yeah.
Try using MS Paint if you're.
So you look up at the top of the screen, it says view options or something similar to that.
Gotcha.
And then there should be something that says annotate.
And what does that let you do?
It just lets you write on it.
Okay. So anybody can write on there?
Technically, yeah, anyone can.
Yeah. But that's, the thing is, I don't know how legible it is, but give it a shot, KJ.
Okay. All right.
Or if you want to do your whiteboard, you can do video.
Okay. Let me go get the whiteboard. I think it'll be probably easier.
Yeah, it might be easier.
Yeah.
Let me go get that real quick.
Okay. I don't know if you have an iPad where you can write on the screen. I don't know if that'll let you write with your fingers. I'm not sure.
Let's see. Can you guys see me?
Not yet. It's dark.
Let me see.
But your video says that you're on.
Right, I don't understand.
You're. Oh, Rebecca's muted.
Yeah, my bird is really loud and screaming, so I'm staying muted.
It looks nice outside.
I think they closed the park by my house, so I can't even go outside now.
Oh, really?
Yeah.
I'm by the Creepcore Lake. I went there Sunday. Like I just drove by. There were so many people. So, which park are you talking about?
Mastodon State Park.
Oh yeah, I know that part.
Yeah, I went hiking there like maybe like a week ago, and normally within like the 2 mile thing, I'd probably see like 2 people normally, and that day I probably ran into like a dozen people, so everybody's just going to the park.
Yeah.
And it's kind of hard to social distance when the path is like 2 feet wide.
Yeah, I know. Yeah. And this by the Creepcore Lake, that's how much space they have, and it was so crowded. I don't know if I'd want to go there. It's that crowded. I need to go one afternoon and see. But now everybody is off, so there's people at all times, I suppose.
Dr. Mary, you want to hear something crazy?
Yeah, go
There
ahead.
was an explosion at my apartment complex last night.
What explosion?
Some guy's car exploded while he was driving. It was like right outside my balcony.
Oh.
And it was 1 a.m. I thought it was like a gunshot or something. And so I got up and I ran downstairs to my roommate. I was like, what is happening? And he was like, I don't know, let's go check it out. So we like went out onto our balcony. And within like the time that we heard the explosion and we got outside, the fire trucks were already there.
Oh, wow.
And this guy's truck was just up in flames. And so we were like, we have to go get a better look. So we like went out and like stood on the street and we watched them put out the fire. And
was his engine just like running wet or something? Like, was it like, did you ever find out why that happened?
No, we didn't find out why.
Why?
Yeah.
I don't know if he had something in his truck that caused it, you know?
It was really strange. And like my roommate and I have been watching a bunch of NCIS. We were like,
oh, I know.
So yeah.
I stopped watching all those FBI files and everything. It's too creepy for this time to be watching all this. Those that were recorded like in the 80s or something, you know, they put it on court TV or something, you know. But was somebody in the truck or was?
Yeah, they were like driving. They were like coming around the turn to come into our apartment complex, and like it was just right there. I don't know why it exploded or how it exploded or what happened, but he was okay.
Yeah, he was okay. Yeah. Okay. Wow, that's crazy.
Yeah.
It's very strange. Probably like John said, something wrong with his engine or something like that. Maybe he had a gas leak of some sort. I
don't know.
Because I mean, like realistically, if there's like a problem with like the amount of fuel going into his engine, like there's too much like gas going in there, and that hits the little flame, like the ignition flame, that could be a problem. You know, because like it's not just like, oh, he's gonna leak gas out of his tank. Like that's not really gonna do anything.
Yeah.
Or that, or too much oil. I don't know. You know, but.
that's scary. KJ, he disappeared on us.
I'm just gonna take a picture and just scan and just show everybody. So.
Okay. Or if you tell me, I can draw it, and you tell me too.
Did the move go well? Get everything settled, Dana?
Which one?
Yeah, we're on. Yeah.
The move, yeah. I don't see any
Yeah.
decorations today. Oh,
I
you're in
have
a
all kinds
different
of
room.
decorations.
Oh, they're behind. Okay.
I got some leaves above me.
Oh, yeah. I see a big teddy bear in the back.
Yeah. I have 2 roommates, but one of them went home to stay at home with her parents.
Did they say anything about your job? Are they closed? Are they doing
Yeah,
takeouts?
they closed like 2 weeks ago, and I haven't heard any plans on them reopening until all of this is over. So
Yeah.
probably not going to have a job for like 2 months.
Yeah, I know. That's the hard part with all of this. And I was asking my other class this morning, Jen Kim, and like, y'all don't get the stimulus package, do you? Because you're students?
I heard something about that, how we don't get
Yeah.
all the money that they're offering for all of this stuff.
Yeah, I know. And your parents can't claim you either, right? Is that right? Or
yeah, I think your kids have to be under 16 for them to add the $500 per child.
okay. Uh-huh. Yeah. Huh. So even if you work full time, would you get it? I think if you are claimed as dependents, then I think you can't. Something like that.
I don't know how that works.
Yeah. No.
I think I read something about they were going based off of your taxes that you filed like from 2018. So,
18. Okay. Or
so
19 if you were
even if you were like a full-time employee right now, but you weren't then.
Oh, then you're okay.
It's really confusing.
Oh, I see. Okay.
That's confusing.
Yeah.
I saw the statistic that like Disney World and Disneyland combined are losing like $30 million a day.
Who's losing?
Closed.
Who? The whole world?
No, Disney World and Disneyland are losing. They lose $30 million a day from being closed.
Yeah, but how much have they made in the last, I don't know how many years?
Enough.
All of it?
Yeah, enough, I think.
Yeah, I don't think they're struggling at all.
No. But yeah, we are capitalistic, and so we want, that's what Trump keeps saying. We want everybody to get back.
Right. And I don't think it'll be, I mean, even though you have like all this money, like if you're not getting any money in and you still have to pay your employees, like you're going to run out of money eventually. So,
yeah. And like small businesses, they have to pay rental, even though they might, part-timers, probably they don't have to pay. They'd have to pay the full-timers to some extent, depending on their contracts, but they have to pay the lease, for the building. And I don't know. Small businesses, I think, hurt the most, not the large ones. The large ones, employees are hurting. Everybody is hurting these days. And you have to learn how to learn on, through online teaching, and I have to learn how to put everything online. I was a nervous wreck 2 weeks ago when we had to do all of this. And so it's a learning curve for everybody. So unique.
My mom was in the process of buying a new house.
Oh, really?
So she doesn't know how all of that is going to go now.
Yeah. So did she find a property or she was just going to look?
She
She
had
had
one.
one?
She put an offer on it.
Mm.
And then they accepted her offer. But like just the whole like family situation, like my dad has to give my mom money to pay for the house. And so like my dad has a lot of money invested in stocks and stuff. And since the stock market is not doing good, he's like, I know. I'm gonna come up with money for you.
Yeah.
So
I know. I didn't look at, because our retirement through MOBAP, they let us, through their financial company, they let us invest in stocks. And the last 3 years, it was doing really well. Everybody was thrilled. And then I didn't look at what had happened until yesterday. And I was like, oh, I'm going to be working till I'm 90. So, and I understand. It's that's why Trump's freaking out. And but there has to be a balance, health and life versus something else. So that's why. And I didn't think our country, the numbers will blow up like this. I was really surprised that some of the big cities are. I mean, you see how fast the virus spreads. It's so quick, and that's the thing. It's
yeah, I heard that we surpassed China and Italy in the number of cases that we have now.
Yeah,
but China's probably not telling their true numbers.
Yeah, because they are a bigger country. I mean, they are bigger than India, I think. I don't know, maybe about the same.
I think they're slightly bigger than India.
Yeah.
They're like densely populated.
Yeah, 1 billion. India right now is 1,300,000,000 people, and so.
I just wish I would have invested in Zoom when all this was going down in China.
I know. Okay, Zoom and Lysol, hand sanitizer. But Zoom, I'm so thankful. And I hope it continues this way because it's been so strong and there's no glitch. And same with Canvas.
Well, my mom said that people were like hacking into Zoom and like hacking into people's webcams.
Really?
Yeah.
Oh.
Which is kind of creepy.
Creepy, I know.
That's why I don't have one.
John's safe. Oh, we have a picture. Thank you, KJ.
All right, yeah, I drew this up really quick. So
yeah,
it might not.
That's fine. That looks good. Yeah.
Okay, so this is the first one. So you can see that there's 3 unique carbons. So you get 2 methyl groups, and then you get a sp2 group. So it's going to be one shown right here in the 150, 100 range, and it's going to be 2 equivalent ones because both of them are equal to this. So it's going to be 2 equivalent CH3 methyl groups right here in 0 to 50 ppm range. All right?
Yeah.
Okay, so now we're going to do the second one. So this one.
Oh, he drew both.
There's no splitting or whatever, so it's going to be 1, 2, 3, 4 unique carbons, right? So we see this sp2 group. It's going to be in the 150 to 100 ppm range. It's 2 methyl groups right here, and it's going to be different. They're going to be different because one is going to be cis to the carbonyl group, and one's going to be trans to the carbonyl group. So they're going to be different right here in the 0 to 50 ppm range. And then it's going to be a carbonyl group right here in the 220 to 150 range.
KJ, I'm not sure if that's going to be cis or trans because there's no double bond there. You see that? Because you can have, remember conformations, Newman, you can have free rotation about that carbon.
Right.
So that's connecting the 2 methyls that you've drawn. So I think they're going to be equivalent. If you had a double bond there, then definitely, yeah.
Okay. So if it's a double bond, then you
Mhm.
got the transit.
Then it
If
makes
it's not a
sense.
double bond, then they're equal.
Yeah.
Got it. All right. So, but I mean, that's all I have. So, you know.
Awesome. Any questions, right? For KJ? And then do you have a fun presentation for your extra credit?
I was gonna show a video
Mm.
about the coronavirus and like
Mm.
you know how you should protect yourself and all, but I
Yeah.
kind of I could put it in, but you know.
Yeah. Well, you can even do it. Jamie's raised a hand. She has a question, but
Okay.
we have to give the others an opportunity.
Okay.
Jamie, is that a question for KJ?
Yeah. I
Okay.
just want to know why that carbon is not circled.
Which one?
There's only 4. What happened to that 5th
I
carbon?
know.
Oh gosh.
We
Okay.
forgot about that, and I forgot about it too.
All right.
You're
Okay.
right. Mhm.
It's gonna be 5 carbons. Yeah, this carbon right here is gonna be SP, so it's gonna go in this range right here,
Mhm.
50 to 100. So it's gonna be 5 carbons. My bad.
Yeah, you're right, Jamie. I didn't catch it. No. So can you all see why should that come between 50 and 100? Why are the methyls between 0 and 50? Can you all explain, everybody? Pull up your chart. Can you go back to the chart, AJ?
Yeah, I got you. Hold on, let me stop share. This.
Deanna, have you pulled up your PowerPoint on your screen? You can do it like this. It'll be easier for you to control it than for me to show yours.
Yeah, I have all my stuff pulled up.
Okay.
Not this one. Oh, hold on.
Yeah, the actual.
Gotcha.
Yeah, that one. So the sp3 methyl. So why did you say, where should those, how will you redraw your structure, KJ?
How would I what? Redraw my structure?
Yeah, where should that where should that carbon that Jamie pointed out, where should it go?
Oh, in the 150 to 100 range, ppm range, because sp2 hybridized carbons go in that range. Oh no, that was sp. My bad. That was sp. So
I thought it's sp3. Isn't it sp3?
Yeah, it is sp3.
is it?
So methine group, where should it go?
So sp3, they should be in the 0 to 50 ppm range.
Yeah. So you will have 3 peaks. Well, one will be because of the 2 methyl groups, and then the third one will be the okay, you need to go back to your structure. We need to make some changes.
Okay. Let me see.
Okay. Okay. How many unique carbons do you have actually?
1, 2, 3, 5.
Okay. Why are those 2 methyl groups unique?
Because they are well, it's no there's no symmetry, right? So so it's going to be they're all going to be unique carbons right here, because this whole compound there's no symmetry in it, so it's all 5 of these carbon's going to be unique.
Okay. And then what about that carbon that you missed? Where should it go?
Since it's going to be sp3, I forgot it's going to be like an H right here too. So,
so it's methine carbon.
Right.
So it should also go there, 0 to 50. Yeah.
Yeah.
All right. Now we'll open it up for questions. Adele, Caitlin. Did you say Shelby? I don't remember.
No, Shelby was good.
So if you didn't say our names, does that mean that we have all of our questions?
Yes.
So yeah, Adele, Caitlin, well, Carly, D, not Deanna, KJ need to ask questions, but you know, KJ can't ask on his own presentation.
Yeah.
Can you do this spectrum with any kind of compound?
Yes.
Organic, you mean?
Yeah.
Yes, any organic compound.
As long as it has carbons, right? Because it's carbon-based. And any carbon compound will have, from mass spec, we learned that it'll have 1.1% of carbon-13 mixed. So, any other questions, even from the other students? Caitlin.
So if you did, if you had one of these charts, and obviously like from the 0 to 50 range, you have 2 peaks in there. Like if you have 2 of the same things, like does it matter? Like do they need to just be close if they're the same, or like because it's a huge range? You're drawing it.
Right, they should be equivalent, so they should be like almost like on top of each other. But I would show like 2 different lines to make sure it's 2 different peaks. So
yeah. So what he says is right. If we had a better table, then we'd be able to say where the methyl carbons are, where the methine carbons are, but they did not. It's not necessary for us to go in detail at this point in time. So for those 2 methyls, you'll draw them close to each other, and then for the methine, you'll draw them a little farther up. And I will ask you to label the peaks, like for the NMR. Like the methyl groups, you would say carbon A and carbon B, and the methine would be carbon C, and then with where the peaks are, you'll label it accordingly. After he finishes, I'll show you.
Any more questions?
Adele? He's gone to sleep. He's gone. Okay. Okay. Adele? Rebecca, take off points from Adele. He's missing in action. Maybe he went to get a drink of water. Anybody else? Even Jamie and others, you can ask questions. Now Jamie did ask a question. Okay, they all know carbon-13 very well. All right, are you going to show that the video or something for extra points?
Yeah, I got.
How long is it? Hope it's not like 15 minutes.
No, it's only 1 minute. It's on YouTube.
Okay. Let's give KJ a hand. He did a good job.
Don't use dark mode on YouTube?
No. Let me see. Explain. Right. So I can find it anywhere. Is this it? No, 7. It was only like 1 minute, and that's it.
You can check your YouTube history if you've watched it.
You can watch that explaining Corona to kids.
Yeah, let's do the kid one.
Yeah, there you go.
Probably heard about coronavirus. Tiny little germs way smaller than anything you can see. It's infecting a lot of people right now. Corona means crown in a super old language called Latin. When you look at it really close, like under a microscope, you can see little spikes with blobs that look like crowns. It causes a disease called COVID-19. That has made some people sick, which can be scary. But there are some things to know. Many people who get it have mild symptoms. That means it's not very strong, especially in healthy kids. There haven't been a lot of kids getting sick so far. It acts a bit like the flu, which you may have had before. We usually see a new type of flu each year. This illness brings a dry cough, fever, and it can be hard to breathe. It might also make you really sleepy. These yucky symptoms are signs your body is fighting it. Your body has an army to fight germs. It's called your immune system. Really smart scientists say people much older are more likely to get phone numbers to call across Canada. Find an adult to help you. If you are feeling really worried about the outbreak, then talk to someone you trust. You might not get to go to school or see your friends for a little while, but know that scientists, doctors, and nurses are working very hard to keep kids and other adults safe.
Is that it?
Yep. And that'll be it.
And that was probably from a long time ago, right? Like a few weeks ago, I would say.
Yeah.
Okay. All right. Thank you, KJ. And before, have you stopped sharing your screen?
Oh, yes, ma'am.
Okay. Now I'm just going to show quickly like I talked about labeling. So if you have a compound like that, I've labeled this as B and this is A and this is C. So when you draw your spectrum, if I ask you to draw, Michaela's coming in. Then you'll say, you'll put the A and the B because they are both methyls. You'll put them close to each other, and then you'll put the C there. Okay. And you don't have to necessarily know whether this should go before or after. We're not worried about that. We're just making it simple. You should find it in that range. All right. So that's what I meant. So then when I go look at your spectrum, I'll know that you place this, in the correct range, and that you put these two together close to each other, and then you put the other one, which is also in that range, a little farther away because it's different from the other two groups. Okay. All right. I know it's not the best. My pen. All right. So I'll stop share, and then I'll let Deanna. You can share. Shelby, what time do you have to go to work? Are you working today?
I was supposed to go to work at 2, but I had someone cover my shift because I've been working like
a lot,
14 days in a row.
Oh my. Okay.
And I have some homework to catch up on.
Yeah, that's right. Okay. So Deanna will talk about UV spectrum, and it's actually chapter 16 in the newest edition, and it's 11 through 13. Sections 11 through 13. Okay. All right, Deanna.
Okay, so as Dr. Mary said, I'm going to be presenting over UV-Vis spectrum. So what is UV-Vis? The UV part stands for ultraviolet, and then the Vis part stands for visible light. We use the spectrum of light in a similar way to other spectroscopies. There we go. That's the word I'm looking for. Like the carbon-13 NMR or the hydrogen proton NMR. And it helps us determine the molecular structure of an organic compound. So this particular one uses 200 to 800 nanometers for the wavelength. So how does it work? The specific spectrum of light is readily absorbed by electrons in a conjugated pi system. So we've talked about conjugation and stuff. So that just means the pi bonds are alternating. These wavelengths have just the right amount of energy to create an electronic excitation that allows for the electron to be promoted to a higher energy state. And this excitation is called pi to pi star transition. And then once excited, the electrons will return to its original energy level and release the energy in the form of heat or light. And then once that energy is released, it's then picked up by the machine and recorded.
Could you hold on there? Now, she has the table to the side. It says sigma to sigma star. So these are all transitions that are explained by the molecular orbital diagram. Remember, we looked at molecular orbital diagram for benzene, and we had all the, remember we did the frost circle and things like that. So we did not go into a lot of details. So there could be, like the orbitals are, if it's from the sigma bond, then you have sigma, and the electrons from the sigma bond going to the sigma star, like it's an excited level. N, what does N stand for? Those represent the lone pairs. So you can have the lone pair of electrons get excited to the sigma star. Or the lone pair of electrons, look at the last one, it can go to the pi star, okay, energy level. But the one that UV catches, UV-Vis, is mostly the pi to pi star and also the N to pi star, okay? So our UV spectrum is going to be in the range 200 to about 600 or so, if you include the N to pi star transitions as well. Pi, you look at the third group, you have the carbon-carbon double bond, you have a pi bond there, carbon-oxygen, carbon-nitrogen, and carbon-carbon triple bond. And the N to pi star, look at those atoms, carbon, nitrogen, and oxygen, not carbon, but oxygen, nitrogen, and well, those are the only two. They all have lone pairs. So their lone electrons will get excited to a pi star level. All right, thanks, Dan.
Okay, and then to get this spectrum, we use a UV-Vis spectrophotometer. And that's the machine that creates and allows the electronic excitation to occur. So it irradiates the compound with a wavelength from 200 to 800 nanometers. And then these wavelengths get split into two beams. So one enters the cuvette, which is just the little glass container that contains the sample that is dissolved into a solvent. And then the other one enters a cuvette that contains just the solid. And the cuvette that contains just the solid is used as our comparison.
Reference or, right?
Yeah, as your reference. And then the intensities of the beams are compared. So a little math. Once the intensities are compared, they're charted based on absorbance. So this is the formula that we use. So A stands for absorbance, and then I sub 0 represents the intensity of the beam that passed through the cuvette containing the solvent. So again, that's your base reference. And then that's divided by I, which is the intensity of the beam that passed through the cuvette containing the sample. And then you take the log of that, and then you get whatever your absorbance value is. And then it gets charted on a graph that looks like this. So in this example, they use isoprene, which is a conjugated pi system, if you look at the structure. And then the graph represents the absorbance values at different wavelengths. And then the top of the peak is called lambda max, and it's the wavelength where you're going to see the maximum amount of absorption, which in this case is 222 nanometers. So some more math. Now we have what's called Beer's law, and it's the molar absorptivity is the UV light absorbed at the max for any compound.
Do you remember Beer's law from Gen Chem 2? You did a Beer's law experiment.
Vaguely.
Vaguely, okay. And you got a, you know, like the max, and then you use the max to get the intensity of light for samples with different concentrations. Okay, but that was visible light. You have a solution that is colored, it's visible. But here, these solutions are colorless if it's in the UV region. Okay.
So we have E equals A over C times L. So E represents the molar absorptivity within that's usually found within the range 0 to 15,000. A represents the absorbance, which we would have calculated using the previous equation. Then C represents the concentration of the solution in moles per liter. And then L represents the sample length in centimeters. So your sample path length is just going to be the length of the cuvette. So some rules and relationships. We've talked about frequency and wavelength and all that. So the higher the frequency, the lower the wavelength, and vice versa. So the longer the wavelength, the less energy you have. So then the longer the wavelength, the longer the lambda max. So you're going to end up with a higher value for your lambda. And then in order to estimate this value, we're going to use the Woodward-Fieser rules.
Deanna, could you go through those relationships, like longer the wavelength, less energy, using the previous slide with the equation shown? Yeah.
This one?
Yes. No, you don't have that equation, but that's okay. Yeah, that's okay. This is from E equals H nu, or what's new? C over lambda. So she's using those equations. That's where she's asking you to recall that relationship. Okay, go ahead, please.
Okay, so for these rules, you start with a base value for your conjugated diene. So that's going to be 2 conjugated double bonds. So your base value for your lambda max would be 217. And then for each additional double bond that's added onto there, if you look at the chart, there's
yes, you have it on the side.
Diene, and then you have 2 extra double bonds on the end. So you're going to add 30 onto your base value for each double bond that's added.
Now, you can look up these. I put up all the tables, and I put a link also on the last announcement that I made, and you should be able to see a similar one. Now, she's going to be doing some examples after she finishes talking about the table, so you should be able to do problems yourself. So that's going to be part of your UV lab, a post lab for another post lab for the UV lab. So you should be able to do that. And so please follow along and know what oxochromic means, what is exocyclic, what is homoannular, diene, and so forth. Okay, go ahead, Deanna.
Okay, so then if you look at the next line down, you're going to add 5 for each alkyl group. So you see you have your conjugated diene, and then you have 1, 2, 3 alkyl groups attached to it. So then you're going to add a net of 15 to your 217 base value. And then you're also going to add 5 for each exocyclic double bond. So a double bond that is in the vinylic position is part of the ring, and the other position is outside of the ring. So again, if you look at the chart, there they have it circled in orange there. So then you're going to add 5 for that one. And then you're going to add 39 for each homoannular diene. So both double bonds are contained within one ring. So it's locked into the cis formation. So then you're going to add 39 on for that, and then plus all of your other substituents if you have them. So I have a couple examples here. And then in the first one, you see your conjugated pi bonds. But this one isn't a homoannular diene, it's a heteroannular diene because the double bonds are not within the same ring. So your base value for that is going to be 214. And then you're going to add on all of your substituents. So here it says that they have 4 substituents. So then you're going to multiply that by 5 and you get 20, which you're going to add to the base value. And then you have an exocyclic double bond. So then you're going to add another 5 and then you get a lambda max that's going to occur at 239 nanometers. And then the same thing for the one on the other side. But this one is homoannular because these 2 double bonds are within the same ring. So then your base value is going to be a little different. And then you're going to figure out all of your substituents, multiply those by 5. And you also have an exocyclic double bond in this one. So then you're going to get a lambda max at 283 nanometers. And then I have this video also.
Would you be able to explain a couple of things? So in both cases, you have 4 alkyl substituents. Could you point those out to us, please? I just want to make sure.
Can you see my mouse on the screen? Can you see my mouse on the screen?
Yeah, we are able to see it. Yeah.
Okay. So this one right here is your first one. So you're just looking at this, what's connected to this right here. So you've got 1 here, and then 2 here, and then 3, 4 there. So then those 4 get multiplied by 5. And you're not looking at these carbons because they're not attached to this conjugated double bond system. And then the same thing over here, because you have your double bonds within this same ring. Mm-hmm. So you're going to be looking at this carbon, this one here, and then this one here.
Mm-hmm. And the
all the other don't matter because they're not connected. Mm-hmm. I mean, they are connected, but they're not directly connected to the pi system.
Jamie has a question. Jamie,
so
go ahead.
It says that there are exocyclic double bonds. Mm-hmm. Where?
Here, let me see if I can go back real quick. Okay. So it says that your exocyclic double bonds are outside. So you have one in the vinylic position that's part of the ring, and then the other is outside of the ring. So in this one, you can clearly see your exocyclic because it's coming off of the ring.
Right, but in the other one, is there one? Because there's like on the bottom it says that, right?
Yeah, this one, if you consider this to be a ring, then you have, the other one is, exocyclic or cyclic. But where do you have 2 here for the structure on the right?
That's a good question.
Mm-hmm.
Oh, I didn't mean to do that.
Okay. Are these from our textbook, or are these from another
these are from an outside source?
Yeah. Okay.
Yeah, just a picture that I downloaded.
Okay. You want to show the YouTube video? Maybe they'll have a.
Yeah. I think I have to stop sharing my screen so that way you can pull it up. Okay. Can you see that?
It's blank right now. There you go.
Can you see the video though?
No. Is it a YouTube?
Yeah.
Let
me see.
You have to play the YouTube and you have to share. You have to share again. Yeah, there you go.
Okay. Okay, so I'm going to pause them after the examples that they give us. So again, you have your conjugated diene, which is going to be your base value of 214. And then you're going to have 1, 2, 3 methyl groups coming off. So then you're going to multiply those by 5, which is 15. So then you just add that to your base value of 214, and it gives you 229. So that one's pretty basic.
Question again.
Okay.
So our chart says that the conjugated diene is 217, and they say it's 214. So which one is it?
Go ahead. I think they're probably using a different chart or something like that. So you go with 217, but assume that that's what, or that's what she's talking about. Got that, Jamie, and everybody? The base value is 217. Like each table will have a slight variation, so that's why it's 214.
Yeah, so then just pretend that's 217 plus 15.
And there could be a variation between cyclic and acyclic and all that too. So, sorry, go ahead, Ian.
Okay. So then for this one, you have your conjugated diene in the dark green again. And you have 1, 2, 3, 4 methyl groups that are in the red that you multiply by 5. But then you have this 4th substituent. I think oh, I thought I had more. Let me rewind real quick. Nope.
So there's a break in conjugation, right, Deanna?
Mm-hmm.
And so that other one is not considered.
Would that not be considered a, what was the word?
You're breaking conjugation. You see, it's not alternate single and double bond. You see that? So that, yeah.
So it's this whole thing is just considered another alkyl substituent. Because, shoot, I keep doing that. Because it's not directly conjugated. You would add the 30 if you go back into the chart. You would add the 30 if it was directly connected to the pi system. But since it's just attached to that single carbon, then that attaches to that double bond, it's just considered another alkyl substituent.
Got that, everybody? Okay.
Okay. So then for this one, again, your conjugated pi system. But since these are in two different rings, it's going to be a heteroannual ring. And then you're going to have this one substituent that they have circled here. They multiply that by 5, and then they call these other ones that are connected to it, they call those ring residues. But they have the same values, so you can just look at them as more alkyl substituents because you multiply them by 5 still. And then this one has an exocyclic double bond.
So you see that one is inside, you know, like focus on one ring, and then the other one is considered to be exocyclic. And so
like if you would block all of this out over here, and just look at this ring and think of it as only having this double bond here and this here, then this one is going to be exocyclic. So then that gets multiplied by 5, and all of that is added up to give you 239. Oh no, it went too far.
you went too far, and KJ has a question.
Yeah.
Okay, so basically we're going to be looking at anything that's allylic to the pi bonds.
Yes, anything that's directly connected to that system.
Yeah, can you go back to that? Yes.
Yeah.
You can explain, right? Yeah. Okay.
Yeah. So this whole green part, this dark green part, is your conjugated pi system again, because you have alternating double, single, double, single, double. And they're all within different rings, so that makes it a heteroannular ring. And then so you just look at your conjugated diene, so you can either pick these two or these two, whatever you want to look at. And then if you look down here at the bottom, it says double bond extending conjugation. And that's where you add on your 30, since you have this whole extra double bond over here that's added to the conjugation. And then all of your red, again, are, they call them ring residues, or your alkyl substituents. And then you have 3 exocyclic double bonds, because if you look at this, if you look at this ring in the middle here, you have one here, then one here, and then if you look at
I know this is the confusing part. So if you look at the one that she pointed to,
both of these circled.
Pardon?
It has two blue circles right here.
Yeah. So cyclic double bonds. So you have 1 and 2. Where do we get the third one?
Yeah, 1 and 2.
I mean, I understand all the alkyl parts. Do you all understand the ring residues? Those are just alkyls. So you look at the red bonds, and you have 5 of them. So that makes sense. And then I understand the double bond extension, and you have, you're supposed to have only 2, that's the base value, and you have a third one, and therefore you add 30. Exocyclic, if you look at this ring in the middle, then you have those other 2. Where is the third one coming from? And what are those 3 circles? What's the circle for on the first one, Deanna? Do you know? Is that the ring she's looking at? Or is she saying that's the exocyclic?
Kicked me out.
Oh, it did. Okay. Your screen froze.
Okay, I'll go back. Okay. Did we figure out where the third one came from?
No. Deanna, do you understand why those blue circles are there? You thought that was because of exocyclic?
Let me rewind it and see if it explains it.
All right.
Okay, so I feel like it's telling me that this carbon here and this carbon here are both contributing.
Oh, okay. Yeah. I see it now. So look at the double bonds, they're all in conjugation, right? So the one she circled, but why does she call it a bond, exocyclic double bond? They should be only, I see, no, I thought I had it, but I don't. I mean, if it's an exocyclic double bond, she should have circled she should have circled the whole double bond. So according to me, there should be 2.
I mean, so, I would think there would be 2.
2, right? Yeah. Okay. So for the time being, we'll assume that there is 2 because that's what it should be. Everybody with me? The exocyclic double bond there, instead of 3 times 5, should be 2 times 5. Because everywhere else, even in the right, the figure on the right, she circled the whole bond.
Yeah.
So
and she circled the whole bond over here too.
As well, yeah.
I don't know why this one's broken up.
That's right.
I have a theory.
Okay.
So I think she is I don't know. Because even in the one on the left, it says 3, right?
No, those are ring residues.
Oh, it says only 1?
Exocyclic double bond.
It's only 1. So here,
which one is that one?
You with the fact that there's another ring attached to here. Because like if you look at this one, there's not another ring on this side of this one. But there's this extra
ring there. So I think she's looking at, that's right.
Because then this double bond would affect this carbon and this carbon. Because if you look at just this as a ring, this is going to be considered exocyclic.
It's double bond, yeah.
Yeah, And then if you look at this ring, then you have these two exocyclic. So maybe that's it.
Then if that's the case, you should look at the first ring and say the one in the middle is exocyclic, you know? I don't know.
Yeah, but the one in the middle here wouldn't be exocyclic because it's not directly connected to this ring or to this ring. If it was here or here, then it would be.
So why are we calling the one to the left exocyclic?
This one?
No, the left, yeah.
This one?
Uh-huh.
Because it's directly connected to this ring here. In the middle. Because it's a double bond coming off of this ring.
Okay.
And this double bond is coming off of this ring. But then this double bond can also come off of this ring.
That's right, that's right. It's all coming back now. Okay. All right, can you, I think we have to start the slide all over. And I think we need to clarify.
Do you want me to go back to my PowerPoint?
Yes. Not to your PowerPoint. This rewind this whole, yes, yeah. Okay. This page.
Okay.
Now go explain the first one, please. One on the left, yes.
This one?
Yeah, yes. Okay, please pay attention.
So the dark bolded green is your conjugated pi system. And then if you break it up into the two different rings, each of these pi bonds are within different rings. So that makes it a heteroannular ring, as opposed to if they were both within the same ring, then it would be homoannular. Mm-hmm. So then all of the highlighted red are going to be your alkyl groups.
Yeah. So put the alkyl substituents and the ring residue all together. Yes.
Yeah. So then you'll have 4 total, because 1, 2, 3, 4. Multiply that by 5. And then you have an exocyclic double bond, because if you look at this ring by itself and kind of block off this part over here, you have this double bond coming off of this ring. So that makes it exocyclic. But this one is not exocyclic to this ring because it would have to be right here. Yes. Or up here or something. It's not directly connected to this ring.
Okay. Do you all understand the exocyclic part for that particular example? Any questions? Raise your hand.
Jamie looks confused.
Jamie did?
I'm analyzing it. I think I get it. I think so, but I'm trying.
It's almost like you have to like take the tops off of these rings and pretend they don't exist.
Right.
Yeah, that's right. Take the top off, make it a convertible. And then, yeah, everybody with me, don't go off to sleep because you have to do problems like this.
I understand.
Okay.
Okay.
And then explain the second one, please.
Okay. So again, you have your conjugated pi system. You can either look at these two as your diene, or these two as your diene, whatever you want to do. But either way, you're going to have an extra one. So it says here that your base value is 214, 217, same difference. But then you're going to add 30 for your extra one, which they do as the last step. To me, it makes more sense to do it as my second step because it's something that really stands out to me.
Yeah.
They can do it in whatever. And then in the red are going to be all of your ring residues or your alkyl substituents, whatever you want to call them, which you're going to multiply. You have 1, 2, 3, 4, 5. We'll multiply those by 5. So then you have an extra 25. And then going back to the confusing exocyclic double bonds. So if you look at this ring here in the middle, you have a double bond coming off right here, which counts as one exocyclic double bond. And then going back, you have this one coming off here, which is two exocyclic double bonds then. And again, this one doesn't count for this ring or for this ring because it's not directly attached. But then this one counts for double because you also have this five-membered ring here, which has this double bond coming off of it. So it's exocyclic to this one here in the middle, and it's also exocyclic to this one. Makes sense?
Did you get the exocyclic part? Everybody? Okay, I think they did. Just hold on, Deanna. I'm trying to draw these without their tops, you know. And then I'm gonna show it here. We'll see if it makes sense. Okay, so could you stop sharing? I'll put mine up on the.
Stop share. There we go.
Stop share. Okay, then I'll do my. Then you explain. This is the first example that you had, the one that I've drawn. So how will you explain this? So the diagram that she had, that had all the closed rings on the side, I removed it. I'm only concentrating on the ones, on the one that is my main ring, and then the others I've drawn as extensions. So how will you do the problem now? What's the base value? She says
217.
Okay, or 214 is what she says. And then how many alkyl groups?
You're gonna have 1, 2, 3, 4.
1, 2, 3. Which ones are you considering? Is it 4 or 5?
Yeah, those two that you circled, or those two that you pointed out.
That's
first.
the base unit.
Yeah.
And I have this.
And 2.
That one.
And 3, and then 4.
That one. Okay. Everybody with us? So that's 4 times 5, 20. The exocyclic is easier to see here. So this is your main ring. Okay. Now, just outside the ring, you should have a bond and a pi bond. Okay. So I cannot have one there because there's a double bond there. But let's say I have one there and I have a double bond there, then that would be exocyclic. Do y'all understand? So exocyclic. I have one double bond. You see, this carbon should be common. Okay. That carbon is common, and out of that goes a double bond. That's exocyclic. And that's 30 units. And then you add these up. Okay. Now, the next one she showed, I've removed all the other cyclic parts that we don't need. So we consider this to be our base. It's 214 or 217 according to us. How many alkyl groups? And then we have an extension, conjugation. That's extended conjugation, or one extra double bond. 1. Okay, one extra double bond. If I had another one here, then I would have to add another 30. Because you see, alternate single, double single, if I had a double there, that would be 2 times 30. Now, how many alkyl groups can you all count? Is this one, Deanna? This one?
Mm-hmm.
Is that an alkyl group?
No.
No. Yeah?
No.
That's not alkyl. This one here. Am I missing something?
And then this one. Yeah, that one, and then the other one.
Off of here?
On the other ring. Yeah.
So it's not this one. It has to be an alkyl, which means it only has double bonds around it. You see that? This only has double bond. Only has single bonds. This only has single bonds. So those are your alkyls. This is not an alkyl group because that has a double bond. So alkyl groups, 5 times, is that 5?
Yeah.
25. Now your exocyclic. So these, you look at all the rings you have, and this is a ring. Remember that exocyclic should have one carbon in the ring and another carbon outside the ring with a double bond. That's exocyclic. One carbon, part of the ring. The other carbon, the next carbon to that is outside the ring with a double bond. So I have 1, I have 2, right? So this ring has 2 exocyclic groups, whatever that is. Now, this ring, okay, this ring has 1 exocyclic bond. So you have a total of, is that 30 or is that 5? How much is exocyclic? 5. So there's a total of 3 exocyclic bonds. Questions? Okay, Deanna, just hold on there. Let me see how many understood. And you may have this example, I'm not sure. Class, this is for you. Okay, there's only one ring. Base alkyl groups. Is there extra conjugation? And then exocyclic. Can you give me values for each one? First of all, give me the total, whoever has it. What's the total?
I got 239.
239.
That's what I got.
What you got? Anybody with a different value?
I got that.
Okay, what's the base value? John, what do you have?
214.
How many alkyl groups?
Are you asking me again?
How many alkyl groups? Yes, I'm
5.
asking you again. 5?
Yes.
5 times 5. Can you label them? Is that 1?
Yes.
Okay. I don't know if he's that 1. Off of this, do you have this one? Or did you?
Yes. Yes.
Are those the ones? Okay. And
Wouldn't it be 6 because you count the
Isn't there one missing?
bottom carbon that comes off the ring? No, on the other side, the methyl group coming off would be an alkyl group to the ring. No, on the bottom.
this one? That's not an alkyl group.
Yeah.
It's not an alkyl group, right?
No, the methyl on the bottom of the ring. Yeah, right there.
Okay.
Because that would be an alkyl group to the ring, right?
Alkyl group to the ring, yeah. That's why they do the residues separate from the alkyl groups. So you have 1, 2, 3, 4, 5, 6.
Wait, say that again. Why that alkyl group we're counting and it's not close to any pi bonds?
Deanna? I think we have to look for an example where they are.
Oh, because it's not directly attached to the pi system.
Yeah, so it should be 5. The 6th one that you have, it's not a ring residue. Okay, that's not considered to be a ring residue. So you look at only those groups that are directly attached to the double bonds or the extensions of the double. So you don't do an extension of an extension. So the thinking was that this is a ring and that you have an alkyl group going outside of the ring. So if I have an alkyl group here, that's not considered either. Okay. So did y'all get the same numbers then, or is exocyclic, something is missing? Is there extra conjugation? So this should be 5. This is 214. Is there extra conjugation?
No.
There's only 2, right? And there's not an extra 1 there. Exocyclic. This is the ring. Now, attached to the ring, you have a double bond just outside of the ring. It's like somebody outside the gate. So that is 5. So what's the total that we have?
234.
234. Is it 234?
244.
Document
244.
part of the image. Just real quick.
Yeah. Let me rewrite it. Let me get another sheet of paper and rewrite it. Okay, I'm going to do it again. Okay. Oxochromic alkyl groups. So your book calls it oxochromic alkyl groups. Those are alkyl groups that are extensions of a double bond. Okay, so if you have an alkyl group, if you have a carbon that's sp3 hybridized, that's an alkyl group. So you have to look at an sp3 hybridized carbon that's directly attached to an sp2 hybridized carbon. Okay, so here you have the base is 214. Number of alkyl groups okay, you should have an sp2 and you have an sp3. I have one sp3 here. I do not have an sp3 there. That's sp2. So it's not considered an alkyl group. Okay, they call it oxochromic. That means you're getting some kind of a light effect from the pi bond. sp2, there's an sp3. sp2, there's an sp3. sp2, there's an sp3. sp2, there's an sp3. Carbon, not hydrogen. Okay, sp3 has to be a carbon here. And we are not looking at any heteroatoms, thank the Lord. All right, so how many alkyl groups have I circled? 5. Now, is there extended conjugation? Meaning, do you have any more past the first 2 on either side? Okay, this is the basic unit. Do I have extended conjugation this way? Do I have extended conjugation the other way? No, not in this case. And then, what's the next one? Our favorite. Exocyclic. Okay, groups. Do you have any? Exocyclic, cyclic, double bond. How do you identify these guys? You should have a ring. Okay, this is our base. Okay, base ring, not the base conjugation. Right outside the gate, you have somebody waiting with a package. Okay, this is exocyclic. Now, if I had a double bond there, do I have an exocyclic group? Yes. Okay. Do I have something like this and a double bond way over there in front of my neighbor's house? That's not exocyclic. How many exocyclic groups do you have? 1, 2. Adele, do you understand exocyclic? Not from the example given, from the example that I've drawn here, there are 2 exocyclic.
Yeah, I get it now.
You get it now? Okay.
Wait, hold up. How many is it? How many is in this example? You said 2?
In the one that I've drawn, which is not the first example on top. Okay.
Wait, so it's not 3 on this one? Oh wait, never mind.
I have a question.
This is the base ring.
Okay. Yeah, I see.
So what is exocyclic to this ring? There's a double bond on the outside, double bond on right outside. That's not counted.
Okay.
So this.
So if you had one
exocyclic groups, there are 2 exocyclic groups.
So if you had one on the bottom next to that one, it wouldn't count either because it's on the bottom base. No, not that one. On the top left.
Here?
If you had one on the top left, it wouldn't count either, would it?
You mean here?
Yeah.
You
cannot have a double bond there because there's a double bond there, right?
Oh yeah.
You can have a single bond.
Yeah.
And then a double bond. This will not be exocyclic because it has to be right outside your door. You see that?
Okay.
I can have one
Yeah.
here.
I have another question.
Jamie, yeah.
So like it just has to be in the ring. It doesn't matter how far away or close it is to the bond. Like it does not have to be right next to it to be external.
To the pi system, like the alkyl groups.
Oh, yeah, it doesn't have to be. The exocyclic doesn't have to be close to that. It has to be like that. If it's a 6-membered ring, apart from those 2 carbons, it can have double bonds at the other carbons. You see that?
Okay. Right.
Yeah. So for the problem that we talked about before, for this example that I had, extended conjugation is 0. For this case, how many exocyclic groups do you have? Just that one. So it's 1 times 5. It's 5 for that. So this is 25, 214, and another 5. So 30 plus 214, that's 244. Now, one thing that this lady in the video forgot, I think, Deanna, she's not talking about homonuclear and homoannular and heteroannular dienes, right? Is she?
I think she has some examples of the homoannular ones later in the video, but she had just been doing the heteroannular ones.
Okay. All right. But in the examples that we've seen so far, are they all homoannulars? Because she's not taken anything into account. I don't remember now, but
they're all heteroannular ones and the ones that she's done. But there was an example of a homoannular one in my presentation.
Okay. All right. Everybody?
Wait, so heteroannular doesn't add anything?
Heteroannular will add plus 39.
No, that's homo.
No, I'm sorry. Homoannular, if both of those are in the same ring, then that adds 39, right? I'll let Deanna repeat that.
Yeah, so you're going to add 39 if you have a homoannular ring, but a heteroannular ring doesn't add anything because they're in 2 different rings. So it doesn't cause as much of an effect as 2 double bonds that are in the same ring.
Right. So here you can write another, I should have put another column. It's so messy. Is there a homoannular ring? Okay. Let me put the picture up. The question is, are both these double bonds inside one ring? Is there conjugation inside one ring? No. Okay. If I have a structure like this, let's do this one. Let's look at the structure. This is the answer to the previous problem. I'll try to hide it. Okay. Can you go through the process? Base value. Let's use our own base value if you want to. It's 214 or 217, okay? And then is there extra conjugation? Number of alkyl groups. And then exocyclic. And then homo annular. Okay, can you answer? I'm going to give you a variation to that one. Give me the total. Hello? Class module, ¿no? Vamos. What do we have? Deanna, you have an answer?
I got 276.
276. Adele, what do you have? Hutch, are you there?
Yes, I'm here.
Okay. Did you get 276 or something else?
That's what I got.
I got
Okay.
276 as well.
All right, great. Caitlin?
I got 276.
All right. Finally, we're all on track, me included. Extra conjugation, none, because there's only the 2. Number of alkyl groups, let's start counting. These are your sp2. How many sp3 carbons coming from the sp2? 2, 3, 4. Did I miss anything? I don't think so. So 4 times 5 is 20. Exocyclic, any? None. Okay. Homoannular. So this is an example where we are seeing both the double bonds in the ring. Okay. The ones we've seen in the past, that's why the ones that Deanna had as well, they did not talk about it because there was only one pi bond in each ring. There were many rings, but there was only one pi bond in each ring. So homoannular, yes, and that is 39. All right. So I'm going to give you a variation to that one. That'll be the last example before Deanna takes over. I don't know what I was trying to do, but you. Okay. Maybe a little tricky. There's no double bond there. Base. Let's do some extensions. I just put one extension. Okay, that's all. Michaela and Becca,
What's up?
did we do this last year?
It looks familiar.
What? You
I don't remember it that well.
Yeah. I don't know if I went over it in detail.
I don't think we went into it in this much detail.
Yeah. The year before, I know I did. It's easy once you know. Just can be a little tricky. Remember who did the UV-Vis last year? All right, what's the base? I'm going to start using 217 from our book. Extra conjugation. Do we have one extra or two extras? John? Sorry.
Yeah, I was wondering about that. So, because the one I think you could count as like an exocyclic double bond, but then with the other one, so I guess I'd say one.
No, don't worry about exocyclic now. I'm talking about extra conjugation.
So could those count as the ones that are inside the ring next to like the second, like the bottom ring? Would those count?
So it has to be an extension. Conjugation, you're looking at these two, right?
Yes.
This is your base, right? Now this is conjugated with that, which means single, double. Now here, single, single, double. Here, single, single, double. So the only extra conjugation coming from that is that one.
Okay.
So this would be, what is it for extra conjugation? Plus 30. How many alkyl groups?
Counted 3.
Counted 3. So this is 1. There's none here. There's 1 here. And there's 1. Where do you have the third one? Coming from here?
Yeah, that one right there.
Yeah. Exocyclic. So this is our base ring. Or this is, the ring. This is right outside of the ring. This doesn't count. Okay. So then you have 1 times 5. Now, if you were to consider that ring, this is outside, that's outside. So you don't have any. So this is 5. Is it homoannular? This is the one that is homoannular. You see, you have those two alternate single and double bonds. This is not alternate and single double bonds. So this is your homoannular diene. So it's 39. I know I made it a little complicated. I'm sorry. But the problems that I'll give you to do as homework will be more direct. I don't want to confuse you more than, you know, this calculation does. Okay, so we'll keep our examples and problems simple. Any questions? It can get wild if we let it, so we'll keep it straightforward. Deanna, do you want to look at a few more examples that you have?
Do you want me to go through the rest of the video?
Yeah. I'll stop share. Then we'll wrap it up fast.
Can I go through more examples, or do you want me to go through the rest of the slides about the sunscreen?
Oh, yeah. Have we looked at enough examples for this one? I think we have. And I'll put up your PowerPoint anyway, so, you know, they can go and view that. What do y'all think, folks?
Muy bueno.
Huh? Okay, whatever that is. Yes, let's keep going. Okay.
Okay. Okay. So if we look at some real life applications for UV light, tanning uses UV light and it produces more melanin that creates a darker skin pigmentation. There are UVA and UVBs present on Earth that come from the sun. Both of these rays are harmful, but UVB is more harmful because it has a higher energy. And then in the presence of UV light, your thymine bases within your DNA, they attach to each other. And then they lead to a genetic code alteration. And then once that genetic code is altered, then cancer cells can form. So that's how you can end up with skin cancer from tanning too much or too much exposure to the sun. So they created sunscreen to protect the skin from UV rays, and there's both organic and inorganic sunscreen. Organic sunscreen will actually absorb the UV rays and then release them in the form of heat. But then inorganic sunscreen just reflects the UV rays off of the skin. So essentially organic sunscreen is more effective than inorganic sunscreen. And then if you have ever analyzed your sunscreen or even used sunscreen, you should have heard of SPF, which stands for sun protection factor. And it's the measurement of protection from the UVB rays. But SPF does not account for your protection from your UVA rays unless your sunscreen contains avobenzone. I've never analyzed the ingredients of my sunscreen, so I don't know.
Have you looked up on your tube or your container?
No, I've never really looked.
I wanted to know the chemicals. Yes. Okay.
All I look for on my sunscreen is that it doesn't have zinc in it because then my sister's allergic to it.
So. Oh, I see. Okay.
Okay, so UVA versus UVB. So UV rays have a lower energy, but they affect skin cells deeper because of their wavelength. So they affect the dermis, which is the layer underneath your top layer of your skin. And then UVA rays are responsible for sunburns, premature aging, wrinkles, and skin cancer. These rays out of the UV, there's UVA, UVB, and UVC, which we'll talk about in a second. But UVAs have the longest wavelength and the lowest energy. Then UVB rays have a higher energy, but they only affect the epidermis, so that very top layer of your skin. And they're responsible for sunburns, blistering, premature aging, skin cancer, and can lead to sun poisoning, which I can tell you from a firsthand experience that sun poisoning is not fun.
Wait, how does that work? If it has like a higher energy, why does it not like penetrate deeper than the UVA rays?
So UVA, I mean, the higher the energy, the more they penetrate. So, so what was your question?
So like, since the UVB has like more energy, wouldn't it like penetrate more?
So the UVB, so look at her fourth bullet point. They have a higher energy. Oh, I see. So she says it only affects the epidermis. I don't know. Why? Do you know? Did you read about it, Deanna?
Like 3 different.
Oh,
it didn't tell me why, but I think.
I'm not trying to be annoying. I just wanted to get my.
No. I thought it was the other way around too. Becca, do you have a answer for that, or somebody started saying something? So, Deanna, what did you read?
I think it has to do with the like your frequency of your wavelength. Because
so the lower energy will have higher wavelength, but also have lower frequency. So like with the, the electromagnetic radiation, radioactivity. So the more the energy, the more they can harm your body, your tissue and stuff. So I was thinking it was the same way, but I think it's the reverse here.
Maybe it's the wavelength, because I guess the UVA rays have a longer wavelength.
Yeah, but why the longer wavelength? I mean, I would think it would be dependent on energy.
Yeah.
Not wavelength, but here it's the opposite. So
I don't know. I'd have to look it up.
Oh wait, maybe, possibly, maybe because it has more energy. I don't know. This might kind of sound stupid, but maybe since it has more energy, like I guess the energy gets absorbed more on the epidermis. Like the top layer. I don't know.
Yeah, I know. We'll all look it up. We'll Google later. But it's good to know. I thought it was the other way too.
I thought it was the other way too. And so the first site that I found, I was like, that doesn't seem right. So then I looked again, and another site said the same thing, and then another one said the same thing. So I was
okay. So it's true, but we don't know yet why that is so.
Another question I have, it's not really for Diana, but like I've noticed like tanning beds, like whenever you use those, like you won't really get like a tan. You'll kind of turn like orange, kind of like Donald Trump.
Yeah, I know. Why is that so?
Like, when you get a tan from the sun, like it looks natural, like it's a brown, like bronze. But I was always wondering, like,
spray tans are what turn you orange. Spray tans are what turn you orange.
Really?
Yeah, even like tanning beds, like when you use those, like you don't really get like, you can tell if somebody got their tan from a tanning bed because they'll look like orange. They won't really look brown.
Well, you have to think about the fact that like the tanning beds use light bulbs, which are essentially man-made UV rays.
Yeah.
And they're not going to be nearly as strong as the ones that are coming from the sun.
Yeah.
Yeah, or maybe they affect the pigments a little different,
Yeah, that's.
Yeah.
I wonder if tanning beds have a special way of affecting the beta carotene that's like in your skin.
Yeah, that's what I'm wondering as to how they. Oh, and they turn you like carrots? Is that what you're saying?
Yeah, well, Kind of, yeah, because like that same like chemical that's like found in like carrots. It's also partially responsible for like your skin per se.
Yeah.
And like that certain color.
I think
Something very
it
similar
does.
to it. So maybe because I know it could also be something that affects your DNA structure within the epidermis. Because I know that UV rays will cause like dimer formation between like the thymine in your DNA.
Yeah,
I don't
she
know
was
if that
talking
has
about that.
but I don't know.
Who knows? There's so many different factors.
Yeah, yeah.
Because it messes up your hair too. It doesn't just mess up your skin.
No, what does it do to your hair?
It can damage your hair, like.
Yeah, like fries your hair.
Because I think your hair also has melanin in it.
Yeah. It can like bleach your hair.
Bleaches your hair. Yeah.
That's why your hair gets lighter in the summer.
Oh, I see. Mine stays the same. It just gets more gray, but.
Okay, moving on.
Discussion. Okay.
So I also mentioned that there were UVC rays, which we don't hear about because there's not a lot of them that come from the sun, and then they get blocked out by the ozone layer. But they are still present on Earth. And oh, I went too far. They have the highest wavelength out of the UV rays, and you find those within like if anyone's ever got a welding sunburn, like I know my dad works with metal and stuff, so he welds, and he ends up with a welding sunburn from welding, which are caused by UVC rays.
They use for welding, they use the blowtorch, which is made out of acetylene gas. So maybe something from the burning of that gas. I'm not sure. Okay.
Okay, so then the last thing I have is another little video that would show you how this spectrophotometer would work in a lab setting.
Hey, cool. We didn't get to do that, so. Is this your extra credit PowerPoint or?
I included both of them as my extra credit. I don't know which one counts.
Yeah, one counts for food replacement, and the other one will be part of your regular extra credit.
So,
All right, that was good. We have a different one. You all must have used it for Gen Chem. It's sort of similar. It's a little box. but we'll get to use it if you take analytical chemistry. Woohoo! Okay. Any questions for Deanna? I think Adele, we can count one of his questions, something that he said as one of his questions.
I had a question.
Go ahead.
Okay, so in all of the examples we used like the conjugated diene value for like the base value. Is there any examples where it's a different base value? Like, or is that just what we're looking for?
Yeah. So if you have a structure that doesn't have the alternate single and double bond, then you cannot do any of the other calculations. Let's say I have one double bond between 1 and 2 carbon, and then another double bond between 4 and 5 carbon, then you cannot do any of the calculations, okay? Because they're so far apart, and you will not have the pi to pi star absorption, and there you'll not have a UV wavelength. Okay, good question. So you must have that base to do anything else. Is that your little cat?
Yeah. Can you see him in there?
Yeah, he doesn't like organic. He's sleeping.
Yeah, he's asleep.
Did everybody answer their questions, Becca, Michaela?
Everyone but Carly, but you know she's not here.
Not here. KJ, does he have to ask a question?
No, I believe he got all the ones he needed.
Okay. So everybody's good. Any other extra questions?
Good job, everyone. That's me.
Yes, very good job. Sorry we took longer. It's just the calculations. I wanted you all to understand the different aspects that you had to calculate. That's why it took longer. And then thanks for staying up, staying back. And so next Tuesday, we'll meet for an hour, or we'll see, we'll talk more tomorrow. I think we've had a long day today. And I just need to do the extension of that carbon 13 that KJ did. So there's a little part to it that I have to talk about and maybe wrap everything up. TAs, any announcements?
I've got nothing.
You got nothing? Will you be able to do those calculations, Michaela? Were you paying attention?
We'll see if I remember it well enough.
Yeah. That's okay. I told them next week or this week, we'll have the unknowns available, and so next week they'll do the unknown lab, and then week after will be the ester lab, and then we'll have to start thinking about giving a quiz. So that'll be the next one. So your labs are pretty, much laid out for you. And so that's our semester for lab. But, oh, there's Shelby's dog. He likes organic. He's listening to me. Yes, doggy, doggy. I don't have a pet, it's just me. All right, guys, thank you so much. Take care. Be safe. I'll see you tomorrow at 12. Okay. All right. And then we'll talk about how to meet fewer times, but a little bit longer. Okay. Bye. Have a good day.